In this video, let us see the finite element analysis of a beam by taking up a solved problem. In order to solve a beam problem, we must also remember the step-by-step procedures involved in analyzing the beam by using FEA concepts. The step-by-step procedures involved in analyzing the beam by using FEA concepts are: first step being discretization of the beam into nodes and elements, followed by second step identifying the degrees of freedom, and third step will be calculating the stiffness matrix, followed by step 4 assembling the global stiffness matrix. Step 5 will be applying the boundary condition, and after by applying the boundary condition, step 6 is the calculation of the unknown displacement. The final step is the calculation of the reaction forces for the entire beam. In order to analyze the beam by using FEA concept, one must remember the stiffness matrix for the beam element. The stiffness matrix for the beam element is given as EI by L cube and its corresponding stiffness values as shown in this slide. Now let us take a beam problem. For a given beam, calculate the rotation at B and C. Take the values of modulus of velocity as 210 GPa and value of moment of inertia I is equal to 6 into 10 to the power of 6 millimeter to the power of 4. As you can see, the support A is fixed, support B, support C is also a roller support, and it carries an UDL load of 12 kN per meter from the support B to C, which spans of 1 meter. After discretizing the beam into elements, now let us see the degrees of freedom of the beam element. The degrees of freedom of the beam element is based on the flexural deformation. Beam will have shear force and the moment at each nodes. The degrees of freedom will be vertical displacement and the rotations. So based on the idea of vertical displacement and the rotations, since we have 3 nodes in this beam, a total of 6 unknowns will be observed for the entire beam. So at node 1, the vertical displacement as d1y and its corresponding rotation as phi1, and at node 2, the vertical displacement as d2y and a corresponding rotation as phi2, and at node 3 the vertical displacement will be d3y and its corresponding rotation as phi3. The corresponding force vector is also given as f1y, f2y at node 2, f3y as at node 3. So step 3 is calculating the stiffness matrix for element 1 with node 1 and 2. So the element 1 will have 4 degrees of freedom, which is nothing but d1y, phi-y, d2y and phi2. By using finite element equation of the beam element, by knowing the values of E, I and L, the finite element equation for the element 1 can be calculated, similar to the equation displayed in the slide, where d1y, phi1, d2y, phi2 are the degrees of freedom that has the nodal displacements and the rotations, and a corresponding nodal force vector which has F1, which will be acting in vertical direction, and the moment M1. Since we have degrees of freedom as vertical displacements and the rotation, the corresponding nodal force and the moment will be observed in force vector in finite element equation. Similarly for element 2, with the nodal displacements and the rotation as d2y, phi2, d3y, phi3 and its corresponding nodal force and moment. This nodal force vector will have forces and the moments for the element 2. After calculating the stiffness matrix for the element 1 and element 2, the next step is assembling the global stiffness matrix. The global stiffness matrix can be assembled in a similar fashion by arranging its nodal displacements and the rotations. The nodal displacement and the rotations are 1, 2, 3, 4, 5 and 6 and its corresponding arrangement in the column wise. So the corresponding stiffness matrix must be arranged by adding stiffness matrix for the element 1 and element 2 based on its location as 1, 2, 3, 4, 5, 6. After assembling the global stiffness matrix, the next step is applying the boundary condition. Applying the boundary condition must be done by observing the support. Since support A is fixed, so d1 y and the rotation phi1 will be equal to 0. If the support is fixed, the boundary condition for vertical, horizontal and the rotation will be 0. So as in the given problem, d1y and the rotation phi1 is equal to 0. Similarly, at the support B, which is a roller support, will have the vertical displacement d2y will be equal to 0. And at support C, which is also a roller support, the vertical displacement d3y will be equal to 0. Since there are no load and the moment acting at A, F1y and F2y will be equal to 0. After applying the boundary condition, in order to calculate the force vector, we need to determine the equivalent load. So the equivalent load can be calculated by using this tabulation. It can also be applied by calculating the general reactions and the fixed moments by observing the external loads. It can also be calculated by using the general reactions and the fixed reaction by observing the external load. So after applying the boundary condition by using a fixed support condition for UDL, the fixed moment and the fixed reactions can be calculated and substituted for the force vector. After substituting the global stiffness matrix and its corresponding displacements and the rotations, and by calculating the equivalent load by using the tabulation or by using the general support condition and the fixed support moments and the reactions, it can be substituted here in the force vector. And based on the support condition, the boundary condition can be applied. After substituting and simplifying the stiffness matrix and the force vector in the by applying the zero boundary conditions, by removing the rows in the column that correspond to the zero boundary conditions, the finite element equations will be simplified as phi2 and phi3. By applying the boundary condition and by removing the rows in the column that has zero boundary condition, the unknown displacements in terms of rotation can be found as minus 1.70 10 to the power of minus 4 radians for phi2 and phi3 as 2.834 10 to the power of minus 4 radians.